Okay, so let us begin. Fine. So, Goa campus, you can see the slides?
Yes, ma'am.
Fine. So, we will continue our discussion, just one more lecture, and then we will be finishing up with common mode feedback circuit design. In fact, design we have done. We have seen how to design a sensing mechanism, a comparison, and then a return mechanism. As I said, so designing is done. But then we need to see that whatever we design, it works properly. So we are looking at some 3-4 analysis. One is the common mode analysis in both feed and without feedback and with feedback mode. So that we are sure that common mode properties are not getting degraded. Second is we have found out the condition for which we can push our desired voltage at the output node. And second is that we need to see that in the common mode operation, we should not get oscillations. My DC should not keep on getting oscillating. Because the loop, when there is a loop, there is a tendency of oscillations. So we want to see that it should not oscillate. It should be a stable value. So we are looking for the third analysis where we see that our loop should remain stable. So what's the condition for that? Remember here our return mechanism is through ISS. Clear? So now as we have the circuitry, again look at the circuit which I was referring to. My reference point would be this circuit. We are assuming op-amp is a single stage op-amp with a single dominating pole. It has a PMOS acting as a load M3, M4. It has input differential transistors M1, M2. There is a beta comparator of gain beta. Output common mode is given to this beta comparator ref given to as my second input voltage. And then whatever VZ comes depending on the comparison between the VOC and VREF, we get which is returned back to M5. And then the loop is complete. Okay. So the VZ adjusts the current through M5 by adjusting its VGS. Okay. So by adjusting the current, we are curtailing that swing that may happen at the common mode. So loop is completed. Now we need to see that under what condition loop will remain stable. Okay. And we know that loop will remain stable only when we have a phase margin, sufficient phase margin. So we are assuming that my gain has a single pole response. Clear? So RC will be dominating. So low pole at this node will be dominating. Pole at the output node is dominating. So it has a single pole response. Rest all other poles, they are non-dominating poles. So this is our assumption. Now remember that in a common mode operation, now in this situation, because it is a common mode operation, we are thoroughly looking at a common mode analysis. So again, as I said earlier, there is a little change. This would be common mode values. These will be both common mode signals. But then in that case, my loop is actually occurring from here to here and then from here to here. This is my loop. Clear? So in this situation, input, if this is my feedback output, this feedback is fed to my amplifier at this node. So according to me, amplifier starts from this point onwards. My amplifier starts from this point onwards. And it produces an output. Here, this output is fed to my beta comparator. It is fed to my beta comparator at this point. So this is my feedback path. Now this is coming into my feedback path. And actually I will consider the whole of this as my amplifier. So with this as the input and this as the output, actually this makes a cascade. Actually, this makes a cascade amplifier. Cascade amplifier with a single dominating pole response. Remember? And with the feedback coming into picture, with this feedback coming into picture, its gain will become now A upon 1 plus A beta. So what is A here? If I ask you, is that of a cascade amplifier? It would be that of a cascade amplifier. So can I say it would be GM5 RO3 roughly? Approximately GM5 RO3 by 2. Approximately RO3 by 2. Clear? So now this is my gain. And if there is a single pole response, what will be the transfer function? A0 becomes GM3 RO3 by 2. A0 is your DC gain of a cascade amplifier. So you write the transfer function for this cascade amplifier now. AS will be A0 upon 1 plus A0 beta. A0 is GM5. Please write down. Goa campus students. Keep on writing as I am speaking and understand why am I speaking like that. So A naught, remember transfer function of cascode amplifier with a single pole dominating is A naught upon 1 plus A naught beta. This is in feedback. Now what is the transfer function for A or A naught? What is the transfer function of A naught itself is dependent on frequencies, open loop frequency response, open loop gain. So what is A naught? A naught is the DC gain, that is minus GM5 RO3 by 2 divided by only one pole is there. So what factor will come in the denominator? 1 plus S upon omega P1, and what will be omega P1? It will be omega out. What is omega out? Tell me. RO3 by 2 into C load. We are assuming R1, R2 very large. What is the dominating pole? The time constant will be R out into C load. Suppose your C loading is CL. So R out will be RO3 by 2 in parallel with the cascode impedance. So now write the full expression for AF. Gain with feedback. Substitute A naught. Substitute A naught. So gain with feedback will be, what is A naught or A? Simple, A naught upon 1 plus A naught beta. Look here on the slide now. Gain with feedback. This is the DC gain. Now DC gain will reduce by 1 plus A naught beta. We all know. So DC gain was initially A naught. A naught was GM5 RO3 by 2. Make it 2. Divide by 2. Earlier it was GM5. Please, as I speak, you concentrate on what I am saying and relate it to what is written in the slide. So A naught is your DC gain GM5 RO3 by 2. With feedback, the DC gain will reduce by 1 plus A naught beta. So whatever is A naught, divide by 1 plus A naught beta. Clear? Divide by the transfer function, it has a single pole. So single pole means 1 plus S upon omega, and omega will be 1 upon R out CL. Remember, omega will be 1 upon R out CL. Now because of feedback, what happens to R out CL? What happens to omega? It increases, so time constant decreases. So look very carefully what I have written. So S upon omega. Omega is, now remember very carefully, omega is 1 upon R out CL, the whole thing multiplied by 1 plus A naught beta. Am I correct? Yes, Srinivas. Are you able to get what I am saying? Kirti?
Yes, ma'am.
So you are able to get the transfer function under feedback conditions. We are assuming that my open loop gain is a single pole frequency response kind of a function. Clear? Beta is your feedback path factor. Now here my beta is composed of only the comparator in this situation. Clear? R out is, now remember RO3 by CL. Everywhere wherever this RO3 written, you make it RO3 by 2. Because RO3, RO4 will come in parallel. Okay? So make it RO3CL. Now substitute R out here in AF. Substitute R out in AF. And rewrite your transfer function under feedback condition. Rewrite. Clear? Done? Okay. Now, I am looking for the stability condition. So, suppose I configure. How do we look at stability condition? We find the phase margin at UGB. We find the phase margin at UGB of open loop gain response. Open loop gain response. Open loop gain response is, now this is, remember this is feedback. Open loop gain response is simply A naught upon 1 plus S by omega, and omega is 1 upon R out CL. So I plot the graph. This is for A. A is A naught upon 1 plus S upon omega, omega out. So this is the graph. Look here very carefully. It is cutting here. It is cutting at this point. This is your UGB. Single pole response, only one pole. This is the gain frequency response of cascade amplifier. Frequency response of cascade amplifier. Clear? Now we have to look for the phase margin at UGB. We have to look for the phase margin at UGB. So at UGB, what is the gain? 1. What is the gain? Gain is 1. Okay? So now, because it is under feedback condition, I need to look at this. For this function. Okay? At S equal to some value, AF is given as, now you substitute everything. Have you substituted everything? So when S is very large, so gain with feedback is 1. At what frequency you have to find out? What is this frequency? Unity gain frequency. What is the expression for this frequency at which gain goes to 1? At which gain goes to 1. We have to find out the expression for this omega unity. And how to find out? We look at this expression. Remember, beta is 1. We have taken beta as 1. Now substitute everything in AF. Please keep on doing. Take beta as 1 and substitute everything in AF. Have you done that? Yes, Salahuddin, is he present? Has everybody done the substitution? Now, I am looking at a value of gain where omega is omega u. And omega u is going to be much larger than your pole frequency. Much larger than your pole frequency. And what's the pole frequency? 1 upon R out CL. 1 upon R out CL. So under that assumption that at omega equal to omega u, now remember S is j omega. S is j omega. So in this omega becomes at omega equal to omega u. What happens to AF? It goes to 1. So at omega, within S is omega u. You have to put omega equal to omega u and put AF equal to 1. And substitute your R out CL beta equal to 1. And substitute your A naught. And take the assumption that at omega u is much greater than 1 upon RO3 by 2 into CL. Make the assumption that omega u is much greater than 1 upon RO3 CL and then simplify. What do you get? What do you get? What is the expression for omega u you get? Do simplification. You have to obtain the value for omega u. You can neglect 1 because you are making an assumption. Omega is much greater than 1 upon R out CL. Magnitude of this function should go to 1 because AF must go to 1 at omega equal to omega u. Yes, Manasa.
I'm still calculating.
Okay, do please do. Because I cannot use document camera, I cannot do it in front of you. I want you to carry out the simplifications. Got it, Manish? Divya, Apurva, yes. Name is? Tathagat. Yes, who has got it at Goa campus? Who has got the expression for omega u at Goa campus? Shriram.
I'm getting minus GM5 by 2 into SCL.
2 because we are converting RO3 to RO3 by 2.
Yes.
Okay? That's why you are getting this 2 factor. But remember, even in A naught, you are getting a 2 factor. I think 2 and 2 should get cancelled out. If I am not wrong. Even A naught will have a RO3 by 2 factor. So that 2 and 2 will cancel out. So omega u should come out to be GM5 upon CL. Has everybody got it? I want an answer from Goa campus. You have to write the magnitude of a complex function. You are taking too much of a time, students. A small simplification, you are taking so much of a time. Okay, Shriram, I give you the responsibility. You will make them understand how to get that expression.
Yes, ma'am.
Because I am not seeing many people getting through. They are still carrying out. Fine. So, if you simplify, you get an expression for omega unity or UGB. It is nothing but UGB. UGB frequency. Frequency at which gain tends to unity. So we get expression for omega unity comes out to be GM5 upon CL. Remember, there would be no 2 expression coming up. As I said, 2 and 2 will get cancelled out. Now, look at this. So at omega unity, it is GM5 upon CL. If you do not have at this frequency sufficient phase margin, then your circuit will oscillate. Then your output DC will oscillate. It will not be a stable value. So we need to look for condition under what? We should get a stable value. Okay. So now let us look at the phase margin. Yes. So how do you now, if this is your, now you have to look for the omega 180 point. Remember, in gain plot we look at the omega or UGB point. At UGB we look at the phase. That phase should be much less than 180. Remember? And if this phase is not much less than 180, what do? We shift UGB where? towards 0 dB, towards left hand side. We shift because omega 180 you cannot shift. Omega 180 you cannot shift. So all you can shift is UTB towards left. Make it less. Make it less. Look here. This is omega unity. And suppose here is your omega 180 point. If this is your omega 180 point, that means your system is oscillating. Because your phase margin will be positive. Positive, or it will be no phase margin at all. So I have to bring omega unity here. If this is my omega 180 point, I have to bring my omega unity here. If your phase margin is beyond this, I don't care, because my loop is stable. So my concern is whether omega 180 is less than omega unity or not. And if it is, then I have to shift my omega unity to less than omega 180, or GX point to be less than PX point. Gain crossover to be less than phase crossover. Omega unity to be less than omega 180. Am I clear? Goa campus. Yes or no?
Yes, ma'am.
So I have to make my omega unity less than the omega 180 in any case. In any case. Suppose it is by default coming, I don't care. But if it is not coming, what can I do? So what should I do? Let me see. So if omega unity has to be shifted here on this point, so that means value has to be reduced. And value can be reduced only by looking at the expression. So either you reduce GM5 or you increase CL. If you increase CL, what will happen to first pole, dominating pole? That will also affect. So that will affect my difference mode operation, frequency response also. I do not want to affect my difference mode operation frequency response. So suppose here I don't change, because it is affecting my frequency response of 3 dB frequency under a difference mode operation. So only thing I can change is GM5. Now GM5 is the GM of ISS current source. And under difference mode condition, this plays no role. This has no role. Why? Because gain is defined by GM1, GM2, RO3, RO4. Nowhere GM5 comes into picture. So I can now use this factor because this will not affect my difference mode operation. Okay? So GM5 I can reduce. So we need to reduce GM5 to shift omega unity less than omega 180. Now how to reduce GM5? Now GM5, what is the expression for GM5? 2I by V overdrive. So can I change ISS? No. ISS means bias current. Otherwise GM1, GM2 will change. On ISS depends bias current. So we cannot change. Can we change overdrive? Yes, but not too much freedom is there. I do not want to change my swing. So actually I cannot change anything here, but still I want a reduction in GM5. How can we do it? So, no, not even W by L. What is done? Now here comes the question, what will happen to the gate source voltage coming from a reference? Remember here VGS we are saying totally controlled by VZ. But actually the gate source comes from a reference current source. Remember. So now here is a solution which takes care of both. I will split the lower M5 into two parts. I will split this into two parts. So I will have two transistors put in parallel. I will split two transistors into parallel. Look here. So 5 is split into two parts. This may carry 80% of the current. And this will carry say only 20% of the current or only 5% of the current. So majority of ISS is controlled by a reference current source. Majority of ISS, which is say 90-95%, is controlled by reference current source. This will come from the reference. Whereas another part which is carrying only say 5% of the ISS. So that total ISS now becomes 100%. But this one carries only say 5% of the current. This is controlled by VZ. This is controlled by VZ. So for my cascode operation, I will not get M51 into picture. M51 will not play any role. Loop will be closed by M52. Clear? M52. So for M52, what's the current? It's only 5% of ISS. That means GM52 is automatically less to ISS. ISS is only 5% of the total value. Okay? So for me, I am able to reduce my GM5, which will be now replaced by GM52. So for the loop that I am making, I am able to shift my UGB towards a lower value. I am able to shift my UGB towards a lower value and achieving stability. And I can achieve stability without doing much. No, not even changing overdrive, not even changing W by L. The moment you put a source degeneration, again there is a swing coming into picture. I want to go for that option which gives you a very little effect or impact on the difference mode operation of my amplifier, op-amp. So you can even go for that process, but characterize it. See how much impact you are getting. But then the moment you put one stack down, the overall swing will get reduced. One more component is coming in the stack. Okay? And in that situation, your entire VGS will be controlled by VZ. I do not want that, because I want my ISS to be stable. So 95% value is controlled by a reference which is stable. 95% of ISS is stable, only 5% is varying. And that is sufficient to give me, because a small change in VGS causes a large change in the current. As a result, my drain voltage, it would be able to control. My VOC, it would be able to control. I do not need a very large change in VGS. And here it will happen through M52. And I will achieve stability also. Okay? So this is the 3 analysis that we have carried out to see that my circuitry still works even when there is a common mode feedback loop. Clear? So we have finished now. Any question that you have in this design, CMFB circuit design. So anytime the VOC takes a swing because of NMOS becoming fast or PMOS becoming fast, this feedback loop will start coming to action. VZ would develop and ISS will be little bit changed, so as to accommodate the NMOS becoming fast or PMOS becoming fast. It will equalize, still equalize the current through both, and it will not allow the VOC to change. Or VOC, we have seen now, VOC I would be able to push my desired value over there. So I am achieving both. Now I know what is my DC level, because I am pushing my desired value. I know the DC level. At the same time, Process variations will not affect the DC level of my circuitry. And loop will be stable, because in any case loop has to be stable. Clear? Is this clear, Goa campus? Any query from the Goa campus? Pilani campus, please ask. And now I am going to shift the topic now. So if you have any question, please ask right now.
Madam, I have a question, but it is not related to CMFP. It is
Okay.
about the measurements. Yesterday when I was designing for ISS current mirror, I couldn't understand how to measure the current from that. Only I have the base. No, ma'am. From at the VP, how do I know what is the current without putting the transistors on top of it? Just the low.
You have to put a dummy voltage source and get the current through dummy voltage source.
Not a resistor, just a voltage source.
Dummy. It should be a dummy voltage source. This is the way how do we do it in this spice. We put a dummy voltage source and we connect it to ground, to the VDD. And we define the voltage at a node of your M5 lower transistor. We define the drain voltage node. Because unless you define, it can take any value because it is connected to VDD. So you have to put initial voltage IC, dot IC command. Initial condition, you have to put what value you want at that node. Because there is no circuitry, you are putting it upwards. You are going to connect it to VDD directly. So 5 volts will come over there or 3 volts will directly come over there, which we do not want. Okay? So you put a dummy source in between the transistor and VDD and then put a initial condition saying that this node voltage remains at say 0.2 volts or 0.3 volts. And then simulate. There is a command, if I remember correctly, dot IC, dot initial condition, which is to be used for forcing a node to come to a certain potential. There may be other methods, you may try, but this is one that I know.
Thank you.
Okay? Fine. So, is this clear? Now we move on to the next. See, this analysis, whatever I have taken the snapshots, you can see it is from a book. So, this is not given in Razavi, this is not given in Alan Moore work. This is given only in Gray and Mayer. Gray and Mayer's book. Authors are Gray and Mayers. And since there is a little bit of confusion, I could not understand so clearly, so I tried to draw my own circuits and then explain it from there. But this snapshot that I have taken is from Gray and Mayer's book. Analysis is there, and you can see in between my slides there are Gray and Mayer snapshots. Okay, these are all Gray and Mayer snapshots. So this is a Gray and Mayer snapshot. So these are all Gray and Mayer, but in between, because I myself could not understand what notations he was using. So I try to draw my own circuits and try to analyze it from that point of view so that I can make you understand what I have understood through that analysis. Okay? So do not get confused that madam is using too many slides. So you can refer to just what slides I have taken in the class. Understand it from there and then go to Gray and Mayer's book. Then move to Gray and Mayer's book. Otherwise, you may get confused. All these things are from Gray and Mayer. This is from Gray and Mayer. Clear? So be very careful. First of all, read from my slides. Because I have made you understand something. Let it go into your mind. Let you get assimilated. And once you understand the concept, then you move to Gray and Mayer's book. Then you will not be confused. Okay. Fine. So everything is done. Now we have designed. Look, we are looking at the design of op-amp circuits. So many issues are coming up. It was not the only gain is a problem. ICMR was there. OCMR was there. DC voltage is there. Biasing problem is there. Reference voltage design. Current mirror design. These all are design issues which come when you design an op-amp. And still there are more issues left that we have to look for. So one by one we are start bringing out each and every issue and we go on enhancing the efficiency of our op-amp circuits. Okay? And now we move on to the next. That is ICMR. How to increase ICMR? What is ICMR? I think we all know. Input common mode range. Remember, it's a folded cascade amplifier. This is input. What's the input common mode range? What all common mode signals you can have? Range you can have, or DC voltages you can have, so that this circuitry will operate. So lower limit for ICMR is VGS plus V overdrive. Upper limit is, this is V overdrive. It has two paths, one here. So V overdrive, another. So this comes to VDD minus V overdrive. So whatever is it, this the drain voltage plus 1 VT. You may say lower limit may have two paths. It is under feedback condition. So one path may be through this, another path through from here to here to here, another path from here to here. Because this node voltage is controlled three paths. One from here, this and this, this and this, and this and this. So we have to see a set lower limit which satisfies all the three under feedback. Without feedback, again you have to find out the all possible constraints and then find out the next. Clear? Now we know if this is 0.7, lower limit is a problem here. If this is overdrive is 0.2, so this becomes a 0.9, 0.7. So 0.9 plus 0.2 gives you 1.1 volt. There is a loss of 1.1 volt lower limit. You cannot have your voltage input DC less than 1.1. There is a loss. I do not want this loss. I want this to be as low as 0. So how do you increase? How do you increase from 0 to VDD or rail to rail? Ground rail to power rail. So that is increasing ICMR issue. And I know that if I use a NMOS differential pair, the lower limit is a loss. And if I use PMOS differential pair, upper limit is a loss. So if you want a rail to rail, why not combine the two together? Why not we combine the two together? So that below 1.1, if NMOS is off, what should operate? PMOS differential pair. Similarly, towards higher voltage range, when PMOS goes off, what should operate is NMOS differential pair. So if you want a rail-to-rail ICMR, all you have to do is combine NMOS differential pair and PMOS differential pair together. And that is what is done here. Look here. And you can easily do this combination in a folded cascade op-amp. Because of folding, input pairs are separated from the output nodes. Because of folding. So you have, this is complete input and this is complete output. This is complete output. So if you refer to only NMOS, it is connected at X and Y and you have a complete folded cascade op-amp. If you take only PMOS, it is connected at these two nodes. And you still have a fully complete folded cascade op-amp. And output point will still be this node. It may be fully differential. You remove this low voltage cascade connection. Or it may be a single-ended output. Hardly matters. I can easily connect both of them together, NMOS differential, PMOS differential in a folded cascade architecture. Very easily it can be done. So that when NMOS goes off for a lower limit, PMOS keeps on operating. When PMOS goes off for a higher limit, NMOS keeps on operating. So my op-amp output will keep on coming between 0 to, even your DC is 0 to VDD. Input DC is between 0 to VDD. But then what happens with both are operating? Because in between range, both will operate. So now we have this problem. Because in between range, so here is something where higher limit, your PMOS will go off. Then NMOS will carry on. So GM of NMOS is shown here. Your gain will depend on GM of NMOS transistors. GMN is shown over here. For lower limit, less than 1.1, NMOS differential pair will not operate, but PMOS differential pair will operate. Then your gain will come to corresponding to GM of PMOS differential input pairs. But in between, the both of them will be operating. And because both of them are operating, GMP and GMN will add together. And your gain will now correspond to twice of that. Total twice GM effect will come into picture because GMP and GMN, each one will produce an output. NMOS as well as PMOS will provide an output. As a result, your gain will no longer remain constant. Though you are able to get a full rail-to-rail ICMR, your gain is varying, dependent on input, common mode, voltage. Gain will keep on changing, which suppose I do not want. Suppose which I do not want. So what should I do? So in that case, in this middle range, can I have some kind of adaptive circuit? Circuit can adapt. That, okay, both are operating. If both the circuits are operating, that is NMOS differential pair is also operating, PMOS differential pair is also operating, then because we still want a gain corresponding to only GM, so make each GM half-half. And you can make each GM half-half by making each current ISS half-half. This is also half and this also becomes half. But when one of them goes to off, then this current becomes full. And when this goes off, this current becomes a kind of an adaptive intelligent circuit. A kind of an adaptive intelligent circuit which changes ISS as desired. Which will change the ISS1 and ISS2 as desired. Okay, in that situation, your gain would remain constant. In that situation, the gain would remain constant. So can you design such circuit? Can you design a block which gives an input to ISS1 and which controls ISS2 also? So that it keeps on changing, it adjusts itself. It adjusts itself. I leave it to you, just try think about it. I will do it in the class also. But then I just want to poke you. Try to think about it, how to do this. I'm not referring to Gilbert's cell. You think on your own. You think on your own. So try to think. I'm giving you one lecture, 2-3 lectures, and then I'll take it up again. Just try to think how can it be done. Come up with numerous ways. Goa campus also. Try to think about it, how you can do it. That you have to make your circuit adaptive. You have to make your circuit adaptive. So your adaptive means you are making it intelligent. It is taking its own decisions. Clear? Just as in CMFB, I am making my circuit intelligent. If node voltage VOC going up, reduce the current. If VOC is going down, increase the current. That's what we are doing. Loop is doing. So some kind of looping is coming to picture. Because depending on the output, you are changing your inputs. To adjust. That is your kind of a negative feedback. Okay? So you have to make your circuit adaptive. I am giving you a time. Think about it. Just think about it. No need to do any analysis. Just think what can be done. Okay, so I am leaving this concept here. And then we move on to the other thing, slew rate. Another issue. Another issue, slew rate. Yes, something which is very important. op-amp has so many design issues. It's not easy to design an op-amp, but we use, remember op-amp like nothing in our labs. We just take mu-C for mu-P 741. 741. No, we use it, put it on a breadboard and throw it away if it is not working. But what is inside is what I'm teaching you here. How do you design something that is inside that? And there are so many issues that people, they have to go through to design a perfect op-amp so that it operates. So slew rate is another issue. Slew rate is another issue. So what is, first of all, let me understand what is slew rate. And why should I be concerned about it? Why should I be concerned? So slew rate is actually how fast your output can change. How fast your output can change. And naturally, it has a bearing on your 3 dB frequency. Because how fast your output can change, if it is not able to change, it will not able to follow a fast changing input. Your frequency response will break down. So how fast, what's the limit? How fast your output can change and where you come across a problem related to slew rate. So let us understand. So normally slew rate affects the settling time of op-amp. What is settling time? Understand. Settling time is that if you give your output, after how much seconds your output is coming. It is getting stabilized. So if your output is, because of negative feedback, if output is ringing, then it is a negative dying oscillations. In how much time? 95% of your value would be coming. Remember settling time graph? You have a tolerance limits, upper tolerance and a lower tolerance. And we say that it takes around 5 tau seconds to come within that band. Your oscillations, they remain within that tolerance band. Do you know? Goa campus, do you know this settling time graph? This settling time graph, do you know this? I am not getting any answers. What do you mean by settling time? Yes. What is settling time? Control system, you must have done it. Control system course. If output is oscillating, then it's a dying oscillations. Then we define a tolerance band. Say 95% or plus minus 5%, plus minus 2% from the top. And the moment your oscillations come within that band, that is the time where we say that output has stabilized. So from the instant input is applied to that instant is your linear settling time. Yes. Have you done this, Manasa?
Yes, ma'am.
Everybody knows there. Nisar, Sriram, everybody.
Yes, ma'am.
Yes. So it affects your settling time. So normally settling time is controlled by a 3 dB frequency. Remember. Normally settling time is controlled by a 3 dB frequency. And that is, that we call as a settling time that is inverse of, that is roughly inverse of the 3 dB. So roughly what we say, remember the signal systems also, there we say that the linear settling time is roughly, we said it's a tau. And tau is 1 upon R out CL. No, tau is R out CL. And omega 3 dB is 1 upon R out CL. Okay, and when there is an oscillation, we roughly say around 5 tau seconds the system stabilizes. 5 tau. 5 tau means we give it a stabilization time because system is oscillating. So 5 tau, roughly around 5 tau. So tau is something inversely proportional to your 3 dB frequency. So tau is the linear settling time. So when we say 5 tau, that means we know that my system is oscillating. So we give it extra time. We give it extra time, we modify it. We modify it. We don't say in tau it is stabilizing, we say in 5 tau it is stabilizing. Where tau is nothing but inverse of 3 dB frequency. So if you know your frequency response, 3 dB frequency is known to you. You can estimate your linear settling time. And if you know how much is the phase margin, your system is oscillating or not, accordingly you can make modifications in your settling time. But slew rate is something there. Even if you know your 3 dB frequency, the settling time that you get will be some other value. It will not be corresponding to 3 dB frequency. That is what happens when op-amp starts slewing or op-amp comes into slew mode. This will start happening. That means 3 dB will no longer control your settling time. Normal small signal frequency response no longer controls the settling time of the op-amp. Why? What happens in a slewing mode? What happens in a slew mode? So this happens, normally it is exponential charge and discharge. We all know. If input is exponential, output also exponentially charging or discharging. Okay? So if you increase your input, output will also increase, because normal equation of op-amp is output equal to gain times input. So if you increase your input, output also increases. If input is exponentially increasing, output is also exponentially increasing. So this is true both in feedback and without feedback. This is correct. This is true. But if you increase your input tremendously high, then something different happens. Then something different happens. And here the op-amp starts slewing. That is why in a cascade of amplifiers, last stage gets a very high input. Why? Because of previous stages they would have amplified the input. So for the last stage, suppose the 3-stage op-amp, the third stage will have a very high input. Magnitude of input would be very large for the last stage, and the tendency for the third stage to move into the slew phenomena. So the slew phenomena may start happening. And the last stage comes to slew mode, entire op-amp comes into slew mode, because output is controlled by the last stage. First 2 stages may not be slewing, but third stage may be slewing. So that makes the entire op-amp to move into a slew mode. So what happens when your input is very large? What happens when your input is very large? Look here. When your input is very large, remember, VGS of this would be very large. And the VGS of this is very large. Means this will have now capability to carry the entire ISS current. That means the current through this transistor will go to 0. So this is as if this path is broken. This path is broken. Can you see the characteristic where you have one current carried by ISS, other current is fully 0. Differential amplifier characteristics. So one path totally goes to off state. And this is the beginning of the slewing phenomena. This causes slewing phenomena. So we will take it up next time.